In this video, we will present ASkDAgger, Active Skill Level Data Aggregation, a novel framework for interactive imitation learning. The promise of imitation learning is substantial. It enables individuals to teach robot tasks without needing specialized coding or robotics knowledge. Despite its successes, traditional behavioral cloning in imitation learning can suffer from a critical issue known as covariate shift. To alleviate covariate shift, interactive imitation learning methods were introduced. These approaches involve obtaining human demonstrations, corrections, and reinforcements interactively. A seminal work in this area is the dataset aggregation, or Dagger algorithm. Dagger works by aggregating human input while the novice policy is executing. Dagger is often combined with active learning, forming what we call ASkDAgger approaches. This strategy offers a dual benefit. It prevents possible failures during interactive training by querying in uncertain or risky situations, and it minimizes the number of demonstrations needed by maximizing their meaningfulness. Existing ASkDAgger methods typically hand over full control to the human teacher when a query is issued. Our work introduces a new paradigm, ASkDAgger, Active Skill Level Data Aggregation. With ASkDAgger, we allow the robot to communicate its planned action when it is uncertain, effectively saying, "I plan to do this, but I am uncertain," and asking if the plan is valid. This allows the teacher to validate or correct the novice's plan. ASkDAgger integrates three key mechanisms that work together to improve learning efficiency and effectiveness. ASkDAgger addresses the problem of determining when the novice policy should act autonomously versus when it should request teacher feedback. It dynamically adjusts the gating threshold to maintain a user-specified target metric, sensitivity, specificity, or minimum system success rate. Next, we have Foresight Interactive Experience Replay, or FEAR. When a novice's uncertainty exceeds the threshold set by ASkDAgger, FEAR enables enhanced demonstration collection by presenting the novice's planned actions to the human teacher. This method significantly reduces the number of required teacher annotations, as the robot can now learn from validations, relabelings, and standard demonstrations. If the teacher deems the proposed novice action plan valid, it is executed and added to the demonstration dataset. Relabeling demonstrations allow the robot to learn beyond instructed commands and potentially generalize better to novel scenarios. Finally, we introduce Prioritized Interactive Experience Replay, or PIR. After demonstrations are collected through FEAR, they are aggregated and a novice policy is updated. PIR efficiently performs these updates by prioritizing the replay of demonstration dataset based on uncertainty, novice success, and demonstration age. ASkDAgger is particularly well suited for mid to high level control tasks, rather than end-to-end policy learning. Since it relies on the novice communicating its planned actions for teacher feedback, the method is most practical for moderate feedback frequencies. It is most applicable in scenarios where a robot has access to predefined parameterized skills, such as grasping, walking, pushing, or screwing. In these cases, the robot novice needs to learn the parameters and affordances of these skills given a user command. We evaluated ASkDAgger across a range of experiments, from MNIST data aggregation to more complex language-based robotic manipulation with clipboard agents, as well as real-world tasks involving engine assembly and sorting with a spot quadruped. To support our claim that ASkDAgger balances query count and system failures by tracking a user-specified metric value, we conducted experiments on interactively training digit classification models on the MNIST dataset. ASkDAgger successfully tracks the desired sensitivity, specificity, and system success rate across various target values. We then moved to more complex, language-conditioned robotic manipulation tasks using clipboard agents in simulation. ASkDAgger showed superior performance on unseen tasks. This is attributed to FEAR's relabeling capability, where novice failures with distractor objects from the unseen set were recast as valuable demonstrations, improving generalization. This was achieved while requiring significantly fewer teacher annotations. This is because ASkDAgger collects many demonstrations through validation and relabeling. To show that our claims extend beyond simulation, we conducted experiments on a real-world engine assembly task using a Franca Panda robot. This robot learned to pick and insert bolts into specific locations based on language commands. The results demonstrate that ASkDAgger enables the system to maintain a high success rate by querying based on ASkDAgger, even while the novice robot is still learning. Similar to simulation, AskDAgger learned from mostly validation demonstrations in later stages and successfully used relabeling in a real-world scenario, further reducing the need for costly annotations. Finally, we showcased AskDagger's applicability by integrating it with Spot's built-in primitive skills to perform a sorting task. This demonstrated that AskDAgger can work with any robot that has predefined parameterized skills such as grasping, walking, and placing. The clipboard agent, trained with AskDAgger, learned to sort objects into waste bins based on commands, using an interactive interface similar to our assembly task. This highlighted AskDagger's versatility in real-world scenarios, leveraging its ability to work with high-level skills. In summary, AskDAgger combines S-aware gating, fear, and peer to balance queries and failures, reduce annotation effort, and boost generalization. It's best for tasks with predefined parameterized skills and moderate feedback rates. For future work, we aim to extend AskDAgger to longer horizon tasks, leverage generative models, and explore its use in hierarchical or high-frequency control. We also plan to study its impact on teacher workload and adapt it to settings with imperfect teachers. Thank you for watching. You can find our code, data, and videos at ASkDAgger.github.io.